Hello everyone and welcome to this video. Please put like in this video, share with your friends needing help in quantum mechanics about operators and commutators, eigenvalues and eigenfunctions. For today we will solve these two exercises. For the first one, we must show that two operators that have the same eigenfunctions commute between them. Eigenfunctions. Operators L and M that have same eigenfunctions commutate between them. Where for this video the new word here is eigenfunction, where before to solve these exercise we will talk about eigenfunctions and eigenvalues of an operator, and also we will solve the second exercise, which is to determine eigenfunction and eigenvalues of this operator and the eigenfunction that we will call psi, and we must satisfy this condition when z is equal to 0 and also z equal to L. And we will also normalize the eigenfunction that we will obtain. Here also the normalization is the other new word that we have. Okay, we go on. Before start solve these exercise, we must talk about eigenfunctions and eigenvalues. Eigenfunctions and eigenvalues of an operator. Okay, on the other hand, we must also talk about linearity of an operator, or also we can say linear operator. And we must talk also here about the ein product of two functions. Okay. Here we will start then talk about the eigenfunctions and eigenvalues of an operator. Suppose that the operator L is acting on a function psi, and as the result of this action we get a number lambda times psi. Then here we say that psi is an eigenfunction or eigenvector of L, and also we call lambda the eigenvalue of L. Here the lambda can be discrete or continuous. Discrete if we have, for example, a set of discrete numbers has the eigenvalue of the operator. Now we can go talking about the linearity of an operator. We say that L is an linear operator if it satisfies these two conditions. Suppose that L is acting in a product of alpha, which is a constant, with psi. If alpha is a constant, then if L admit that we can take out alpha and L acting only on psi, then this is the first condition of linearity. And the second one, if L satisfies this first condition, then, and we have C, for example, has a sum of two products here, F, alpha 1 times F, alpha plus alpha 2 times G, for example, then if L act on the function C, this means that we have as a result alpha 1 times L acting on F plus alpha 2 L acting on G. Okay, then we say that L is a linear operator. We go on talk about here. It's very important also, we can use here this definition of linearity to show about the inverse of eigenfunctions. Suppose eigenvalues of an operator. Suppose that we have M acting on function psi, so that we get mu times psi. The question is, what is the eigenvalue of the inverse of the operator M? But we know to answer this question, we must remember that the inverse of M times the M must be equal to the M times the inverse of the M, which is equal to the identity operator, where here identity operator means that if this operator acting on the psi function, we get psi function, we get again psi function. Now we can follow to try to obtain the inverse, the eigenvalues of the inverse of the operator M. M is acting on psi and we get mu times psi. Then if you apply the inverse of M in this product, we get, now remembering that this is equal to mu times psi, and we have the inverse of M times mu times psi. And because M is the inverse of M, if M is linear, then its inverse is also linear. Then we can take out the mu, and we have mu times the inverse of M times psi, or acting on psi function. Okay. On the other hand, we have here we are saying that this action is equal to this result. On the other hand, we know that M times M acting on M must be equal to the identity acting on M, because this product is equal to identity as we can see here. And if we have this identity has equal to this, which is also equal to this identity, then we are saying that this expression must be equal to this one. And here, remembering, we must have only psi. We go on saying that then psi is equal to mu times the inverse of m times psi. And also, if mu is different, if mu is different to 0, then we can take this mu to the left hand side, and we get inverse times psi equal to 1 over mu times psi. This means that if m acting on psi, we get mu times psi, then its inverse, applying its inverse, we get 1 over mu has the eigenvalue. Okay, we go on talking now about the inner product. What is actually inner product? Suppose that we have two general functions, psi and, for example, phi. Then the inner product, if we are only working in one dimension, for example in x direction, then we have that the inner product of these two functions we write as, we use the bracket, which is equal to integral of psi complex conjugated times phi, which is in x direction, times d of x. This is this is the inner product between these functions. Also, if we have, for example, if we change the position of these two functions, we have then this inner product must be equal to the phi complex conjugate times psi here times d of x. On the other hand, if psi is equal to phi, then we have that psi, this inner product, is equal to complex integral of complex conjugate of psi times psi d of x, where this is the square of module of psi, where then this we call probability density. And we know that if these represent the probability density, the sum of the integral, this integral must be equal to 1. And we call this the normalization condition. Here. Normalization condition 1 is equal to the integral in the whole space of the square of the module of x d of x. Okay, this is the normalization condition. Okay, now we can go on try to solve the first and the second exercise. The first exercise is show that if two operators L and M have the same eigenfunction, then those operators commutate between them. Okay. We have L acting on psi, and we get lambda times psi. On the other hand, when we apply the M on the same function psi, we get mu times psi. This means that the psi here are the eigenfunctions of L, also of M. On the other hand, we have the eigenvalues that are generally different. Okay, now we can say that when we apply M to this action, we get here, remember that is lambda times psi, and we have then M times acting on lambda times psi, and M must be linear operator so that we can take out the lambda and we have M acting on psi. And we know the action of M on psi, we get mu times psi. That this means we have now lambda times mu times psi. We can also, this we can call A, and we have B here. We have also L acting on M acting on psi, and we have, as the result here, we have mu times psi, and L has a linear operator, gives us the possibility to take out the mu, and we have only sorry, L acting on psi, and here we have mu times lambda times psi. Here we must remember that lambda and mu are also numbers, which means that when they multiply to each other without considering the order, we will get every time the same number. That is, this product is equal to this product, so that these full expressions are equal, which means that these first expression are also equal. Then we have here A has equal to B, so that M acting on L acting on psi is equal to L acting on M acting on psi. And if we take this to the right hand side, we get L acting on M acting on psi minus M acting on L acting on psi, which is equal to 0. And here we can take out, we have psi has the common, and we can take out, so that we have M minus M times L time acting on psi has equal to 0. By definition, we know that this is a commutator between L and M, which is L commutating with M acting on psi, which is equal to 0. But if psi is different, to 0, then we have the commutator L and m has equal to 0. Then we showed here that if if L and M have the same eigenfunctions, then they commutate between them. As we have talked in the previous video, this means that we can observe experimentally the eigenvalues we can observe experimentally both operator at same time at same time for in only one experiment. Okay. Now we go on to trying to solve the second exercise, which is determine the eigenfunctions and eigenvalues of this operator and normalize the eigenfunction. Then here for the second exercise, we must try to solve minus the square acting on psi, and we will say that we must get square of lambda has the eigenvalues of this operator and times psi, or I can say here we are calling L has minus d square over d of z, and we have the eigenvalues for the possible eigenvalues of the L operator has the psi of z, and we must get has the eigenvalues lambda square times psi of z. This means that minus the second derivative of psi in function of z must be equal to lambda square times psi of z. Okay, as we can see here, we have a second order differential equation, so that we can write this expression as the second derivative of psi of z plus plus lambda square times psi, and this equal to z. Here we can solve this exercise using two ways. Here we can see is the second order differential equation with constant coefficients, so that we can take as our solution written as L their power k times z and times z. And here we have that the first derivative of this is k, where k here is a constant, no? Yeah, we have k time k time L their power k times z, and the second derivative is k square time L their power k power times z. Then we substitute this expression for the second derivative in this expression, and we substitute this one for the psi the psi function in this, and we have now k square plus lambda square, or both time k times z has equal to 0. We know that this is every time different to 0. No every time, but okay, we have here this has different to 0, and we have then that this expression must be equal to 0. Then k squared is equal to minus lambda squared, so that we have now k has equal to plus minus square root of minus, which is equal to plus minus I lambda. Here I will take I will only considering that lambda is a real number and is non-negative, so that we have has the solution. We can write now our solution has the linear combination of these two possible solution, which is c of z has equal to a times Euler power minus I lambda times z, remembering that here k is equal to this expression and we are substituting in the respective position in our function, plus the other constant b times I lambda times z. This is our possible solution. But we must remember in here that psi must be equal to 0 when z is equal to 0 and also when z is equal to L. And okay, we must remember this as the condition of the frontier, the boundary condition. On the other hand, we must also remember that Euler power minus I lambda z we can rewrite as cos of lambda times z plus minus I sine of lambda z, and also I power Euler power I times lambda times z, it's equal to cos of lambda z plus I sine of lambda z. So that if we substitute these two expressions in this relation, we can rewrite psi now. Psi of z has equal to a0 cos of lambda z plus a1 sine of lambda z. This is the other way to write our function. Then now we can go on using our boundary condition. We must have z when z is equal to 0, we must have the function has equal to 0, which means a0 times 1. Here I can write as 0 plus a1 sine of lambda times 0, and we know here we have 0, so that the sine of 0 is equal to 0, and here we have 0 and cos of 0 is equal to 1, so that here we have a0 has equal to 1, and we only have psi of z has equal to a1 sine of lambda times z. Then we can use now the second boundary condition, which is z equal to L must gives us the function psi has equal to 0, and we have this as a1 sine of lambda times L. here we must remember that if psi is equal to 0 when z is equal to L, and this means that or a1 is equal to 0, or then sine of psi of lambda times L is equal to 0. And we know that if a1 is equal to 0, this means that psi will be every time equal to 0, but this is not the case that we need here, and we must guarantee that only sine of lambda times L is equal to 0 in this situation, so that sine of lambda times L is equal to 0, and we have here the only values that lambda times L must have to get the sine has equal to 0 are the multiple of the integer multiples of pi. Then n times pi must be equal to the lambda times L. Here, remember that n is equal to 0, 1, 2, and so on. Because when we have 0 has the argument of sine, we have sine of 0 equal to 0. On the other hand, we have also sine of pi equal to 0, sine of 2 pi equal to 0, and so on. Okay, then this means that lambda, where now we will put the index n, where n is these representing on only these n number, must be equal to n times pi over L. This is something that we call the quantization condition. The quantization condition. Okay, which means that lambda, the eigenvalues will not take will every time take integer numbers of a specific number, fixed number, which is equal to pi over L. Okay. We go on now. We have that. We have now psi of z has equal to a1 times sine of lambda n, which is n times pi over L times z. This is our eigenvalue, eigenfunction with this eigenvalues. These eigenvalues, and this is eigenfunction, or also eigenvector. Okay, we can also put here n to represent the different value for n. On the other hand, we don't know until now the a1. The a1 is the normalization constant. Has the last equation has is to normalize the eigenfunction, which means that we must obtain a specific value for this constant. Then the normalization condition, as we have saw in this video, 1 must be equal to integral of the density probability here times d of x, or in whole space. And here we must remember that we are defining our function between x between 0 and L, and we can visualize this as, for example, a square. Here we can visualize this as a wall where we have here x equal to 0 and here x equal to L, but our potential is equal to 0. Yeah, okay. Then this, we must take the integration between 0 and L. If we take, here it's z, also here z. Okay, then if we take the square, or the square of module of this function, we have then 1 has equal to a1 square integral between 0 and L of sine square of n times pi over L times z d of z, and we can rewrite this sine square as 1 over 2 1 minus cos of 2 times n pi over L times z d of z. And now, as the result of the integration, we get a1 square over 2 of z minus L over 2 n p sine of 2 and p pi over L times z between 0 and L. As we know, if z is equal to L here, we simplify L by L and we have only 2n pi, which is equal to 0. Also, if z is equal to 0, we have sine of 0 and we get 0. This means that this first term is equal to 0. But if we substitute here, L has equal to z has equal to L, and we have only a1 square over 2 times L and we have 2 over L has equal to a1 square, and we have a1 has equal to square root of 2 over L. This is the normalization. The value of the normalization value, so that now we have the full wave function written as square root of 2 over L times sine of n pi over L times z. Thank you for watching this video. Put like in this, share with your friends, subscribe in our channel if you are not subscribed in our channel, and see you on the next video. Bye.